Hey guys, welcome back to another round of chemistry notes. In this video, we are going to talk about how to draw covalent Lewis dot structures. Last video, we learned about ionics, and this one we'll learn covalents. So remember that Lewis structures, and specifically covalent Lewis structures, illustrate how chemical bonds hold molecules together. And remember, covalent compounds are nonmetals that share electrons to get up to 8 valence electrons. So the structure for your Lewis structures, the element symbols, just like before, the element symbols represent the nucleus and the core electrons. The central atom, this is a new thing, the central atom is the atom in the center that all of the other atoms are bonded to. And then all of those outer atoms are called terminal atoms. And the terminal atoms surround and bond to the central atom. There are a couple of different things you can see in a Lewis structure. Besides just the element symbols, you may also see pairs of dots, dot pairs, on single atoms. Those are called lone pairs because they belong to one single lone atom. These are not involved in bonding. They're just kind of along for the ride. You will also see lines which represent bonding electrons. The lines are involved in bonding. The lines are the bonds. So one line represents one pair of electrons. One line is a single bond. Two lines, two pairs of electrons. Three lines, three pairs of electrons, triple bond. So here's an example. This is, of course, water. So we have oxygen here in the center. This is your central atom, is the oxygen. We have two terminal atoms. Those are both these hydrogens. So this hydrogen is a terminal atom. This is a terminal atom. We have two lone pairs. This is a lone pair and this is a lone pair. So those are not involved in the bonding at all. Those just belong to the oxygen atom. And finally, we have two single bonds. There's this one right here and this one right here. So those are sort of your different pieces of your Lewis structures. As far as drawing your Lewis structures, first, you need to arrange the atoms. You should put the lowest electronegativity in the center because the central atom is the one that's going to have to share with everything. So it should be the one that is the best at sharing, the one that's the least greedy, the one with the lowest electronegativity. So lowest electronegativity will go in the middle unless it's hydrogen. Hydrogen will never be the central atom for reasons that we'll see in just a little bit. So once you've arranged your atoms, you'll draw the Lewis structures for each individual atom. Before you try and connect anything together, you'll just draw each individual Lewis structure. And then once you have all of your Lewis structures drawn, you will use a single electron from two different atoms to form a bond between them. And you'll continue forming bonds until all electrons are paired. Remember, electrons are needy. They travel in pairs during bonding, so you're never going to have just one single electron all by itself. It'll either be paired up with another in a bond, or it will be paired up with another as a lone pair, but it will almost never be by itself. If you're drawing a polyatomic ion, if you're drawing something with a different number of electrons than it should have, there's one additional step. If it is For positive ions, remember positive ions, those are cations. For positive ions, you need to remove electrons, and you will do that from the central atom first. If you have negative ions, those are anions, you will add electrons to the central atom. And once you have done this, once you've messed with your number of electrons, you'll enclose the whole thing in square brackets and include the charge, just like we did for our ionic compounds. And then the last thing you need to do once you've drawn your structures is check yourself. You need to make sure, does every electron have a partner? Does every atom have a full octet? And have you used the correct number of electrons? This one at first will seem really obvious, and then we'll see some exceptions that show you that this is not always super clear. So it's always a good plan to double check, make sure you've got the correct number of electrons. In order to do this, you count up all the electrons that you used, including in the bonds. Add up all the bonds, all the lone pairs until you've counted all the electrons. And then add together the valence numbers of all the atoms that you used and make sure that these numbers are the same. The only electrons that you're allowed to use in bonding are valence electrons, and you got to use all the valence electrons. So you should add up all of the lone pairs and all of the bonds, and those are all of the electrons you were allowed to mess with. When you add up all of the valence electrons you started with, that should be the same number because those are the only electrons you're allowed to change. All right, so quick review on numbers of valence electrons. Let's practice some individual Lewis structures first. So here is hydrogen. If you look on your table, it is in the first group, which means it has one valence electron. Since it only has one valence electron, it can only contribute to one bond. You can only form as many bonds as you have electrons to form them with. The electrons make the bonds. So this only has one valence electron, it can only make one bond. Next we have beryllium. If you look on your table, beryllium is in group 2, which means it has two valence electrons, which means it can make a bond right here and it can make a bond right here. So it can make up to 2 bonds. If you find boron, it's over on the other side of your table. It's in group 3, means it has 3 valence electrons, which means it can form up to 3 bonds. Carbon is in group 4, so it has 1, 2, 3, 4 valence electrons. It can form up to 4 bonds. Nitrogen is in group 5, which means it has 1, 2, 3, 4, 5 valence electrons. So you might be tempted to say it can form up to 5 bonds, and sometimes elements with 5 valence electrons can do that. We'll see that in a little bit. However, nitrogen only has 3 single electrons. It can form a bond here, or here, or here. These electrons here already have a partner. They're already paired up. They really don't want to go find new partners because that's already done. Why do the extra work? So nitrogen ideally will only form 3 bonds. It can form more than that, but it prefers to form 3 bonds. Oxygen has 1, it's in the 6th group, so it has 1, 2, 3, 4, 5, 6 valence electrons. So it's got a single electron right here and a single electron right here, and if it has its choice, it's going to make 2 bonds. It can form more than 2, but if it gets to choose, it's only going to make 2. It'll use this electron in a bond and this electron in a bond, and that's it. And then fluorine, one of our halogens, has 7 valence electrons. So we've got fluorine, 1, 2, 3, 4, 5, 6, 7. So fluorine has one single unpaired electron. Ideally, it's just going to make this one bond right there. Again, it can form more. These electrons can split off to make new bonds, but if it's already paired, it prefers to stay paired. So these are the preferred number of bonds. It does not have to be like this, but this is sort of the most natural arrangement. This is the preferred number of bonds. You will see exceptions, but this is the most common layout. All right, let's take a look at some examples here. We're going to practice drawing Lewis structures. So we start with CH4. We're going to follow our steps. Step 1 says to arrange the atoms, which means we need to figure out what is our central atom and which are our terminal atoms. Well, a couple of ways to figure this out. One, generally, if you only have one of a thing, that is the central atom. Also, it should be our least electronegative element, which would be hydrogen, but if you recall, hydrogen will never ever be the central atom. One reason for this is that hydrogen can only make one bond. It's a pretty crappy central atom if it can only bond to one other thing. So we're going to put carbon in the middle. Carbon right here, and put our 4 hydrogens just around it. So this is our arrangement. Now we'll go ahead and draw the individual Lewis structures. So carbon has 4 valence electrons. Just like we saw in the last slide, it will look like this. So we can put our 1, 2, 3, 4 valence electrons on carbon. And then each hydrogen has 1 valence electron. So we'll put 1 valence electron on each hydrogen. Step 3 says to use a single electron from 2 different atoms to form a bond. So we have to connect each of our atoms together using our bonds. So we can use this electron and this electron to form a bond between this hydrogen and this carbon. So we can sort of connect these into a line to show this is a bond here. And then here as well, we have this electron and this electron right between these 2 atoms. We can connect these 2 together into a bond. We've got an electron here and an electron here between these 2 atoms, so they can connect together into a bond. Electron and an electron will connect together into a bond. So we've connected all of our single electrons. All of our electrons have been paired up. Now it's time to check ourselves. Does every atom have a full octet? Well, carbon has 4 bonds on it, and this bond is 2 electrons. And this bond is 2 electrons, and 2 electrons, and 2 electrons. This carbon, since it's sharing all of these electrons, gets to count them all. So this is 2, and then 4, and then 6, and then 8. So carbon does have a full octet. It's got 8 electrons. Each hydrogen only has 2. I'm going to tell you now that that's okay and ask you to go with it, and we'll talk about it in a little bit. So carbon has 8, that's good. Each hydrogen has 2, which is actually what we want. So let's make sure we've actually used the correct number of electrons. Remember that carbon has 4 valence, and then each hydrogen has 1, so that's another 4 in total. So we should have used 8 electrons drawing this structure, and we have used 2, 4, 6, 8 electrons drawing this structure. So this is all set. It is a little messy. That's okay if you want to leave it like this, or we can practice just drawing it the way it should be, which is like this. And you will probably reach a point where you don't need to draw the dots individually and then go back and color them in. When you reach that point, it's totally fine. This is a completely acceptable and honestly more desirable final answer without all of this middle work. But while you're still getting used to it, this is a really good step to take. Okay, looking at our next one here. We've got CH2O. Step 1 is to figure out the central atom. We know it cannot be hydrogen, so it's down to carbon or oxygen, and we should choose the less electronegative one, which is carbon. So we'll put carbon in the middle, and we'll sort of arrange our hydrogens, our two hydrogens, and our oxygen around it. Then we'll draw each individual Lewis structure. Carbon is 1, 2, 3, 4. And then hydrogen is 1, and oxygen is 1, 2, 3, 4, 5, 6. So we'll go through and start connecting electrons like we did last time. These two here, pretty obvious, will pair up to make a bond. These two right here, pretty obvious, pair up to make a bond. These two right here, pretty obvious, will pair up and make a bond. And then we've got this awkward electron over here and this awkward electron over here. So these will sort of move into the middle between the carbon and the oxygen. So they will disappear from, down here, and will instead form another bond here in the middle. So then we have paired up all of our single electrons. Every electron has a partner, right? 2, 2, 2, 2. Those are all pairs. And then we've got a lone pair here and a lone pair here. So everything's paired up correctly. Each hydrogen has 2 electrons and 2 electrons, which we've said is what hydrogen likes to have. Carbon here has 2 and then 4, and then this is 2 and this is 2. So that's 2, 4, 6, 8 electrons. Carbon is good. Oxygen has 2, 4, 6, and 8. So oxygen is good. Last thing is to double check, make sure we've used the right number of electrons. So carbon has 4 valence electrons. Each hydrogen has 2 valence electrons, and oxygen has 6 valence electrons. So 4 plus 2 plus 6 is 12 electrons, which means we should have 12 electrons in our structure. And let's count. 2 in this bond, 2 in this bond, 2 in this bond, 2 in this bond. So 2, 4, 6, 8. And then 10 and 12. So we've used the right number of electrons. I have sort of made a mess of this, so I'm going to go ahead and redraw it a little neater. Carbon in the middle, bonded to a hydrogen, and then a double bond to this oxygen, which also has 2 lone pairs. So this is what your sort of end result should be. So we've got 2 single bonds, 1 double bond, and 2 lone pairs hanging out in this structure. Let's take a look at our next example. Our next example is a little odd. These won't come up super often, but I do want to sort of show this to you. Sometimes you don't have a central atom per se. You kind of have 2 central atoms. All right, so our first example, N2H2, we can follow our same steps. We'll start by figuring out our central atom, and we know it cannot be hydrogen, so it's got to be nitrogen. So we'll put nitrogen in the center, put our other nitrogen as a terminal, our 2 hydrogens as terminals. Then we'll go ahead and draw our Lewis structures. So 1, 2, 3, 4, 5 on nitrogen. Then again, 1, 2, 3, 4, 5 on this nitrogen, 1 on hydrogen, and 1 on hydrogen. And then we can start connecting bonds. So this will be a bond right here, and a bond right here, and a bond right here. Easy enough. And then we've got these 2 leftover electrons right here that don't have partners. So we can sort of force them to pair up. We'll move this one over here and just pair these 2 together. There we go. All right, so now we've got everything paired up. We've connected all of our bonds. Let's go ahead and check ourselves. Does everyone have the number of electrons they want to have? Hydrogen has this bond, so that's 2. Hydrogen has this bond, so that's 2. Nitrogen has 2, 4, 6, 8. Nitrogen has 2, 4, 6. problem. That's not great. Maybe we lost some electrons somewhere. So let's just see if we're like missing some electrons. Nitrogen has 5 valence electrons, and we have 2 of them to start with, so that's 10 here. And then hydrogen has 1. We have 2 of those. That's 2 there. So we've got 12 electrons to start with, and we have used 2, 4, 6, 8, 10, 12. Well, that's not great either. All right, so we've used all the electrons we are allowed to use, and 3 of our atoms are good. They've got the right number of bonds, the right number of electrons. This one right here is the problem child. So what we can try to do is move some electrons around a little bit. We can bring this electron and put it right there, and this electron and put it right here to form a double bond. I'll get rid of that and get rid of that. And then even just ignoring for a second the fact that now we have this random electron here and this random electron here, this nitrogen is going to have 2, 4, 6, 8, 9 electrons. It's a mess. This problem is a mess. So here's what you need to know. Sometimes you will follow all of your steps and you will follow all of the rules and you'll get to the end and it's just not right. Check your work, double check your math, type it in the calculator if you have to, and when you just really cannot make it work, realize that sometimes some molecules have weird shapes and just go back to the drawing board. This is one of those times. Every once in a while, you're going to get a molecule that has 2 central atoms. Or put another way, no central atoms. And they form more of a line than a clump. So if we put our 2 nitrogens in the middle and then follow the rest of our steps, nitrogen is 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, and then each hydrogen is 1 and hydrogen is 1. We can follow the same steps we've been doing now, and it's going to work out pretty well for us. We'll form a bond right here, and a bond right here, and a bond right here, and then these 2 will move into the middle and form a bond right there. And we will end up with nitrogen double bonded to nitrogen, each of those single bonded to a hydrogen, and then each nitrogen has a lone pair. And if we check this out, we've paired all of our electrons. We have used 2, 4, 6, 8, 10, 12 electrons like we said we would. And this is our final shape. Again, this is a rare case. It's not going to happen all that often. Just be aware that sometimes you'll follow all your rules and not end up where you want to be. And at that time, maybe consider rearranging your structure. All I'm saying about that. All right, let's move on to something a little bit more normal. We have NH3 here. This is ammonia, like the house cleaner. Obviously, hydrogen can't be the center, which means nitrogen has to be. So then we will arrange our 3 hydrogens around the outside. And we will draw our Lewis structures. 1, 2, 3, 4, 5. And each hydrogen has 1. So then we can go in and connect our bonds. Bond right there. Bond right here. Bond right there. That one's significantly easier. Everything's paired up. And we have 2, 4, 6, 8 electrons that we have used. Nitrogen has 5. Each hydrogen has 1. So 3 hydrogens give us 3. 5 plus 3 is 8 electrons. Everything is all set there. And if we wanted to just draw our structure like you will normally see it, just like that. Usually a lot more straightforward than this guy over here. This is sort of a weird exception, problem-solving kind of case. Problems like this will be much more common. All right, 2 more together before you have some to work on your own. Okay, here we have NH2, and it's very small, but it does have a minus. So what this means is we're going to have 1 extra electron to work with here. So, same steps as always. Central atom goes in the center. So that'll be nitrogen still. arrange your hydrogens on either side, and draw your Lewis structures. 1, 2, 3, 4, 5. 1 electron here, 1 electron here. We'll go ahead and connect the things that should obviously be connected. So we'll form a bond right here, form a bond right here, and now something weird has happened. We've used all of our electrons, but it kind of just looks like we're missing one right here. That's where this negative comes in. If this compound has a negative charge, that means we have 1 extra electron. We should have 5 from the nitrogen and a total of 2 from both of our hydrogens plus our 1 extra electron. So that's 5 plus 2 is 7 plus 1 is 8 electrons. We should have 8 in our structure. And at this moment, we have 2, 4, 6, 7. So this is a really easy problem to fix. We can just throw 1 extra electron in right there, and we're done. We've got nitrogen in the center, bonded to a hydrogen on each side, and then 2 electrons on our central atom. We need 8 electrons in total. We've used 2, 4, 6, 8. Nitrogen has 8. Each hydrogen has 2. All set there. All right, last but not least, we have Pi3, finally getting some different elements in here. So between these two, phosphorus is going to go in the center. It's our only one of that element. So we'll put phosphorus in the middle, and we'll put our 3 iodines around the outside. Then we'll draw our Lewis structures. Iodine has 7 valence electrons. So we'll draw 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7 on each of our iodines. And then phosphorus should be 1, 2, 3, 4, 5. So we've drawn each of our Lewis structures. Then we will go ahead and start pairing up electrons. So we'll pair these right up right here. We'll pair these up right here. We'll pair these up right here. And that's actually all we need to do to make sure all of our electrons are paired. Everything else already has a partner. So let's make sure that everything has the right number of electrons. Starting with this iodine on the left, we have 2, 4, 6, 8. Good there. This iodine on the right, 2, 4, 6, 8. This iodine at the bottom, 2, 4, 6, 8. And then our phosphorus, 2, 4, 6, 8. So all good there. Last thing to double check is to make sure we've used the correct number of electrons. So we've got phosphorus starting with 5 valence electrons, and each iodine starts with 7 valence electrons for a total of 21 coming from there. So we should have 26 electrons in our structure. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Looks like we've done it all correctly. I've made a big old mess of this, so I'm going to draw it one more time. We should have phosphorus in the center with a single bond to an iodine, single bond to another iodine, single bond to a third iodine, and 1 lone pair on the phosphorus. All right, so that is our last example to work together. On the next page, or at the bottom of the page, you will find some practice. Go ahead and work through those 6 practice problems on your own. Remember, there is one sort of weird exception kind of problem, so if you run into it, follow the steps we talked about, consider rearranging your structure. And when you're ready to check your answers, you can check out the key on my website. You get them all right. Excellent. Nice job. Let's move on and talk about exceptions to the octet rule. So I sort of touched on this a minute ago. Some elements require fewer. Some elements actually require fewer than 8 valence electrons in order to be stable. So the one we've seen over and over so far is hydrogen. Since hydrogen only has the 1 valence electron, it only needs a total of 2 electrons. It only needs 1 bond in order to be stable. Our next exception is beryllium. Since beryllium only has 2 valence electrons, it's only going to form 2 bonds for a total of 4 electrons. And then if you're good at pattern recognition, you might already know what the third one is. That's going to be boron. Because boron only has 3 valence electrons, it can only form 3 bonds, which means it only needs 6 electrons. So those are your 3 elements that require fewer than 8 electrons. There are also some elements that are capable of holding more than 8 valence electrons. They don't have to hold more, but they can. And when you have elements holding more than 8 electrons, it's called an expanded octet. This is only possible for elements in periods 3 through 7. And that is because those extra electrons are stored in empty d orbitals. If an element does not have d orbitals, it can't store extra electrons. So your expanded octet elements can hold up to 12 electrons, 6 bonds. See a couple of examples of that. All right, our first example here, we have BeH2. Hydrogen cannot be in the center, so we'll put beryllium in the center and surround the hydrogens on either side. Then we'll go ahead and draw our Lewis structures. Hydrogen has 1 valence electron and 1 valence electron. Beryllium has 1, 2. So once we've arranged our atoms, we can start connecting bonds. We'll connect one right here, and we'll connect one right here. All of the electrons are paired up now. We can check each hydrogen has 2, because each hydrogen has a single bond. Beryllium has 2, 4, which is what we wanted. Double check, make sure we have the right number of electrons. Beryllium started with 2. Each hydrogen started with 1 for a total of 2. Makes 4 electrons we are allowed to use. And we have used 4 electrons. So that is our Lewis structure for this compound. Moving on to our next one, we have SF6. So we're going to have sulfur in the middle, surrounded by 6 fluorine atoms. Go ahead and just space them out kind of evenly. And then we can draw our Lewis structures. Sulfur has 1, 2, 3, 4, 5, 6 valence electrons, and each fluorine has 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So those are all of our Lewis structures drawn. Now we can go ahead and pair up our single electrons. We can form a pair right here, pair right here, and a pair right there. And now everything is paired, but we have not formed enough bonds yet. So this is where the expanded octet comes in. Sulfur is in the 3rd period. It is capable of forming an expanded octet. So you'll notice we have 1, 2, 3, 4 fluorines left that we have not connected to this sulfur. And this sulfur has 1, 2, 3, 4 electrons still on it. So we are actually going to split up these paired electrons and form a bond right here, and a bond right here, and a bond here, and a bond here. And that means sulfur, instead of having 2 bonds and 2 lone pairs like it normally does, is just going to have 6 bonds from its 6 valence electrons. So drawing this a little bit neater, go got sulfur bonded to 1, 2, 3, 4, 5, 6 fluorines. We can double check ourselves, make sure we've used the correct number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. 48 electrons. And sulfur gave us 6, and each fluorine gave us 7 times 6 is 42. We had 42 electrons to use. Everything has its full octet, and this is what sulfur hexafluoride looks like. All right, 2 more. Our next RnCl2, we're going to put radon in the center because it's our lone element. We will surround it with our 2 chlorines. So each chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then radon is a noble gas. It's going to have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. This is not a trick question. You're probably thinking, Ms. Childs, it's a noble gas. It's not going to bond with anything. And no, it generally won't, but that doesn't mean you should just not draw the structure. We're still going to draw the structure. So we will have our bonds form just like we're used to. This chlorine has to bond to something. Radon doesn't have any unpaired electrons, so we're going to have to split up a pair. This electron will bond right here. This chlorine has to bond to something. It'll bond to this other electron right here. We can sort of rearrange this a little bit. We will have radon in the center, bonded to a chlorine on the right, and bonded to a chlorine on the left, and then with 3 lone pairs on the center. So each chlorine has 2, 4, 6, 8. 2, 4, 6, 8 electrons. It is happy. Radon has 2, 4, 6, 8, 10 electrons, which is a little weird, but okay. Radon is in the 6th period. It has empty d orbitals to store electrons in. So the last thing to check for is to make sure we've used the correct number of electrons. We should have 8 from radon plus a total of 14 from our chlorines to give us 22 electrons. And we have used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So we're all set, and this is what our structure should look like. Okay, last one. We have BF3. We're going to put our boron in the middle, least electronegative, and the only one of its kind. And then we will give it its 1, 2, 3 valence electrons and surround it with our 3 fluorines, each with their 7 valence electrons. And then we will start connecting lonely electrons into bonds. So we'll form a bond right here, form a bond right here, we'll form a bond right here. So that takes care of all of our unpaired electrons. Everyone has a partner now. We should double check, make sure fluorine has 2, 4, 6, 8. Fluorine has 2, 4, 6, 8. This fluorine has 2, 4, 6, 8. And this boron has 2, 4, 6, which is what it wants. It wants to form 3 bonds. So then our last thing to make sure of is that we've used the correct number of electrons. So boron gave us 3, plus each fluorine has 7, so that's 21 electrons from fluorine, which gives us a total of 24 electrons. And we have used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. So our final structure is boron bonded to our 3 fluorine atoms, each with their full octet. All right, at this point, you've got some practice drawing your own Lewis structures and then answering some questions about expanded octets and bond strength and all that good stuff. So go ahead and do your practice. When you're done, you can check the key on my website. And at this point, you know everything you need to do your first quest assignment. So you can go ahead and get started on that or head on to the next video, whatever you want to do. In any case, good luck and happy studying.